So I'm just going to give a old-fashioned chalk talk. Let's see if I can remember how to do this. So let me see. I want F to be a field. I want to recall something that's completely classical. I think fundamentally important for huge parts of the math that we all do. Probably very familiar to all of you. Let me see. I need to fix some positive integer L, and I'm going to write L as n plus n prime. So I'm going to be talking about Grassmannians, and my Grassmannians are going to be an n-dimensional subspace of C to the L. So that's what L and n are doing for you. I write sim L for the algebra of symmetric polynomials. So this is just polynomials in L variables invariant under the symmetric group SL. Okay, so sim L, that's just symmetric polynomials of rank L. Sitting inside symmetric polynomials of rank L, if you, instead of taking full invariance of the whole symmetric group SL, you just take partial invariance for that maximal parabolic subgroup Sn cross Sn prime. So just permuting the first n and the last n prime of the numbers 1 through L. So this algebra of partial invariance, and let's get my arrow going in the right direction. How about that? Full invariance sits inside partial invariance. So this is what? This is sim n tensored sim n prime, just tensor product of those two algebras, kind of in the obvious way. So sim n is the first n of the variables, sim n prime is the last n prime of the variables. And I think a fundamental theorem is that the embedding of sim L into sim n tensor sim n prime, this is a Frobenius extension. So there's just so many things that kind of rest on that basic algebraic fact. Maybe I should just recall what that means. There's a trace going in the other direction. So there's the inclusion in one direction, and then there's a trace going in the other direction, but from here onto this subalgebra, which is a sim L module homomorphism. Everything's commutative here, so I'm just talking about modules rather than left or right. And there are dual bases. So let me see. Actually, the bases we're in this very classical situation. So these are bases as sim L modules. So this guy is free as a module over sim L, and there's a pair of dual bases for sim n n prime as a sim L module. One of them consists of Schur polynomials, S lambda, for lambda being a partition that fits in an n by n prime rectangle. So there's my lambda. And the other basis, so this is a Schur polynomial on the first n variables. This is in this sim n part. So as lambda ranges over all partitions that fit in that n by n prime rectangle, this is one basis for sim n n prime as a free sim L module. And the other basis is just do the same, but put a Schur polynomial in the second n prime variables, these S mu's. And mu here should be a partition fitting in an n prime by n rectangle. Let me see if I can draw a mu like that. And these are dual in the sense that if you take the product of the first basis S lambda tensor 1 and the second basis 1 tensor S mu, and then you apply this trace, you get up to some sign, you get a delta function depending on if lambda and mu match, you get plus or minus 1, otherwise you get 0. And lambda and mu matching means that if you take lambda and you take mu and you have to kind of flip mu around, because this is the n by n prime rectangle, you have to sort of transpose mu and put it in the other corner. Matching means they exactly fit to cover the entire n by n prime rectangle. When that's the case, this trace of the product is plus or minus 1, otherwise it's 0. So there's these dual bases. Of course, the explanation for this comes from geometry. If you take this sim n tensored sim n prime, take this algebra, and if you specialize, so you tensor over sim L with the ground field, just viewed as the trivial representation of this graded algebra sim L, everything's commutative. So this is just a quotient of sim n tensor sim n prime by an ideal, and it's just the ideal of invariance in all L variables of generated by the invariance of positive degree. So this is well known, and this is just the cohomology algebra of the Grassmannian of n spaces in CL and working with coefficients in F. And so this sim n tensor sim n prime being a Frobenius extension of sim L, when you specialize sim L to the field, that just makes this specialized algebra into a Frobenius algebra over the ground field. And that's clearly explained because this is just the cohomology of the Grassmannian, and the Frobenius structure comes just from Poincare duality. If you remove the specialization and just focus on this algebra, which I think I'm going to denote from now on by HNL to make you remember that it's some cohomology, this is actually equivariant cohomology of the Grassmannian, not torus equivariant, but equivariant with respect to the whole reductive group GLL. Okay, so that's the classical recollection. Maybe I should also just write down what trace is explicitly here. So this magic trace, this sim L module homomorphism from the big algebra projecting onto the subalgebra, it's actually given. All you do is you take F. Take your polynomial in sim n prime, and then you have to multiply it by some monomials, these kind of staircase monomials. You have to multiply x1 to the n minus 1, x2 to the n minus 2, all the way down to xn minus 1 to the 1, xn to the 0. So this is sort of a monomial in the first n x's. Kind of this is the weight row in the indices there, and then you take what you do x n plus 1 to the n prime minus 1 all the way down to x n plus n prime minus 1. So this is another one of these staircase monomials in the last n prime variables, and then you apply tau. This tau, this is de Maizière operator, longest element of the symmetric group SL. That explicitly gives this trace. So these de Maizière operators do the work. Okay, so that's everything that I want from kind of classical stuff. This crucial Frobenius extension, it appears all over the place. For example, if you like Zergel bimodules, this is sort of at the heart of the theory of Zergel bimodules, this extension. So what I want to do is talk about an odd super. I kind of use the two words interchangeably. Some people don't like the word super and they prefer the word odd, and it depends what you are. Analog of this. So what we're going to do is that I'm going to take, well, let's just start off with the usual polynomial algebra, but now I'm going to view as Z2 graded, the generator X is an odd variable. Okay, so that's all I'm doing. I'm taking the usual polynomial algebra, but I'm making it into a super algebra, a Z2 graded algebra, just by declaring that X is odd. I'm not letting X squared equal 0 or anything like that. It's just ordinary polynomials in X with a Z2 grading, so X is odd. And I'm going to work with what I'm going to call O pol n, odd polynomials of rank n. Actually, I want to do L to match the above. And all I'm going to do is I'm going to take L copies of that of the rank 1 odd polynomial algebra. And so the X in the first tensor position I call X1 and so on. And the X in the Lth tensor position I call XL. Except this isn't the usual tensor product of algebras. This is now the braided tensor product of superalgebras. So in the braided tensor product of superalgebras, when you try to multiply A, B, and C, D, it's the first tensors and the last tensors, but you have the braiding when you pull the B past the C, and we're working in the category of vector superspaces. So you have to times by, if both B and C are odd, if both parities are 1 in the ring Z2, then you get an extra minus sign cropping up. That's the tensor product we're working with in this braided setting. So the upshot of this braided tensor product in this odd polynomial algebra is just that xi xj is minus xj xi, for I different from j. That's all that goes on when you work in this world. So this is slightly non-commutative. This ring O pol L, this super algebra O pol L. It's kind of very mildly non-commutative. The x's themselves, the x squared is not 0. That's something people often think I'm doing. This is not super commutative. This super algebra I'm working with. So then the analog of the algebra of symmetric functions sim L that I had before. This is odd symmetric functions. O sim L is just simply defined as the subalgebra. Well, it's got lots of different ways of describing this. For example, you can take the subalgebra generated by the odd elementary symmetric polynomials. I'm sure this notation is familiar, ER, and you all know what ER is in ascending order. It's the definition of the rth elementary symmetric polynomial. It's just these x's are odd, so now this is the odd elementary symmetric polynomial. You just take those guys for all r, they generate a subalgebra of O pol, that's called O sim, the odd symmetric polynomials. So this definition was worked out about 10 years ago by Ellis, Khovanov, Lauda. I think it was around about 2013. This is what I'm setting up for you now. Now, you don't just, instead of generating by these odd elementary symmetric polynomials, you could just as well generate by the odd complete symmetric polynomials, HRs, and the definition of these is almost what you would expect, except you've got to take your monomial in descending order now. I've got greater than or equals, whereas here I had strict less thans, but I've changed the order. So these are descending monomials. Those are the odd complete symmetric polynomials. Kind of part of the story in this game is that you see things are mildly non-commutative. It's kind of important that you put these in the correct orders to get this working out. It's not completely obvious that these generate the same subalgebra of O pol as these guys, but you can quite easily see the transition between these two sets of generators are just like in the classical case. This is sometimes called the infinite Grassmannian relation. And so indeed, the H's do generate the same subalgebra as the E's. But there's also another family of odd elementary symmetric polynomials, which I call epsilons. What I've done is I've changed the less thans to greater thans. Now, it's easy, because these x's anti-commute, it's easy to see that you can completely flip one of these strict monomials, and all you get is a minus sign r choose 2, so that these and these are just equal up to a sign. And if you prefer, you can work with those guys. The kind of Roman e's and h's, and then the Greek epsilons and etas on the other side. So these are the similar Greek versions of symmetric polynomials, find in the same way. It's really not obvious that these guys, the relation between these is not so obvious, because remember, if all of these are distinct, you can anti-commute. But if you have squares or cubes, you don't. There's not. So when you reorder these using anti-commutativity, you don't get just these guys up to a sign. So the relationship here is much more subtle than the relationship here, and it seems a bit weird that I would even mention it, but it's kind of the price you pay for being mildly non-commutative is that throughout the theory, there's kind of two parallel stories, elementary and complete, and I call these dual elementary and dual complete.
Interaction of SL, but you don't have the invariance for SL?
I have not. I'll try and fix that in a minute. So I've given you a very bad definition, just artificially defining it as the subalgebra generated by these random polynomials. And so it looks a bit unjustified right now. But just before I do that, there's the E's and the H's and the epsilons and the etas. There's also an algebra involution, which I call gamma. It's sort of, I kind of think of it as a sort of a graph involution. And it interchanges e's and epsilons and h's and etas, and all it does, it just sends the first x to the last x, and so on. So that obviously switches these two guys. It obviously changes the order around when you apply that. So no big deal. So okay, so Jill wanted a better definition. To give a better definition, so we'd like some kind of invariant definition cutting out OSIM as a subalgebra of O-pol, and you can't define it in any way as invariance. That's not quite the right point of view. But what there are these odd analogues of de Maizière operators, which I call tau i's. In the even case, instead of defining sim as symmetric polynomials, you can also define it as the intersection of the kernels of all the usual de Maizière operators. And that's the right point of view that carries over to this odd world. So I need to quickly tell you what these odd de Maizière operators are. So these are defined quite easily. First of all, I'll tell you what they do on xj's. You get 1 if I equals j, you get -1 if I plus 1 is j, if j is I plus 1. And then, so that tells you how to do it. So these guys, by the way, these are of degree -2. I always put my x's in degree 2 in this story. These de Maizières are of degree -2. So they're linear maps, and they apply them to 1 and you get 0 because that drops you off the bottom. Apply to any of the degree 1 operators, you get 1 or -1 or 0, depending on j. And then in general, you need to know how to apply them to a product. Absolutely not. So this is a theory where everything's bigraded, z and z mod 2. So it's kind of another hallmark of what goes on in this world. So let me see, it's Si of f, tau I of g. So it's a sort of twisted Leibniz rule. This would be exactly how you define ordinary de Maizière operators in the even world. The difference is that Si here is not quite what you think. It's an algebra automorphism of O-pol, and Si of xj, well, it's xi plus 1 if j is I, it's xi if j is I plus 1. So it's switching xi and xi plus 1, but then it's minus xj in all other cases. So that minus sign is the only place that's kind of different in the setup from the classical story. And so that's odd de Maizière operators, and it gives us this kind of intrinsic definition of odd symmetric polynomials. So it's kind of a slightly weird analog of ordinary theory. So now you have this invariant definition. Of course, you can now work out what you mean by OSIM n tensor OSIM n prime. So you instead of taking all tau i's, you skip tau n, and you just intersect the kernels of all of these except I equals n. And that gives you this natural analog of what we called Sn cross Sn prime invariance before. And if you take, so this guy in OSIM L sits inside OSIM n tensor OSIM n prime, just as you take the extra kernel of the tau n and you get this guy cut out as a subalgebra. So this is exactly analogous. And now the first question you ask in this odd story, is this a Frobenius extension into an analog of my fundamental theorem in this odd world where things are just anti-commuting rather than still a map in the other direction, a trace map projecting OSIM n tensor OSIM n prime onto OSIM L. I'm not going to write down the definition because I think I already did. I still got my trace map somewhere. There. Exact same formula gives you a trace map in this world. It's just that you have to use the odd de Maizière. Now you've got to be a little bit careful because these odd tau i's, they don't commute when I and j are far apart. The ordinary de Maizières, they satisfy the usual braid relations of the symmetric group and they square to 0. These odd de Maizière operators, they square to 0. They don't satisfy quite the braid relations that you're expecting. They satisfy the braid relations up to a sign. And so that means that when I mean de Maizière per logos element, I actually have to, that's ambiguous up to a sign, and you have to just be a little bit careful and specify you fix a choice of longest element, but it's not a big deal. Gives you this, I'm not going to care anyway. These dual bases is always up to a sign, so it's really not important to get that precise. So there's a little bit of a choice. Still have this trace, and there still are a pair of dual bases. There are these S lambda tensor ones, the lambda in the n by n prime rectangle. And before I just looked at one tensor S mu's. Actually, it turns out you have to look at so the S lambdas are in this world, they're odd analogues of Schur polynomials. So they're called odd Schur polynomials. And they're, from the right point of view, they're defined in the same way. And they were worked out by Ellis, Khovanov and Lauda a decade ago. So these guys give a basis for OSIM n prime as a free right OSIM L module. So you've got to be careful, things aren't commutative anymore. So I've got to distinguish left modules from right modules. So they're still free as a right module. These odd Schur polynomials, whatever they are, give a basis as lambda ranges over the n by n prime rectangle. And then on the other side, you have to actually not take the Schur polynomials, but the dual Schur polynomials, so I switched to Greek. That just means I apply my gamma, my graph automorphism. And these guys, mu in the n prime by n rectangle, give a pair of dual bases as before, as right OSIM L modules.
Yeah, these SIs, they do generate an action symmetrically.
They do, yeah, they do.
But these elements are not invariant.
Sometimes they are, but in general, it's the wrong definition to call this invariance of these SIs. That's not quite what's going on. In rank 2, that's actually correct, but above rank 2, it's not. So I've got this kind of weird odd analog now of this classical embedding, this Frobenius extension, which is this kind of shadow of Poincare duality in the even story. And in the odd story, there we go, we've got natural analogues of these algebras, and we even have a trace map, and we've got these dual bases, and everything's free in the right way. But there's a catch, because now things are not commutative. This trace map is a right module homomorphism, but it's not a left OSIM L module homomorphism, and so this is not a Frobenius extension. Even when L is 2, you can easily see this is not Frobenius. There's no complement to the image of that as an OSIM L bimodular. So you feel like you're stuck at that point. You kind of introduced this weird new odd analog and expecting to get this Frobenius extension, and it simply doesn't work. But there's a fix, of course. Fix is to specialize a little bit. So instead of working with all of OSIM L, I'm going to call RL. This is kind of going to be my ground ring. It's going to be this odd symmetric polynomials of rank L, and I'm going to factor out the two-sided ideal of all odd elements. Actually, it's just enough to factor out the first elementary symmetric polynomial you want. So that's just the sum of the variables x1 plus up to xl. Once you kill that, you kill all the other odd elements. No, I mean, so the ERs generate this OSIM L, and the problem is they don't commute. Yes. There is a complete set of relations between them known, and it's kind of rather subtle. 2 even ERs commute and 2 odd ERs commute. But there's this rather weird relation between an even and an odd guy. And this was discovered by Ellis, Khovanov and Lauda, and you look at it and it's quite unpleasant, but it's kind of good enough to do things like straighten words in the ER. So you can see that it's got the same, I mean, you know, it's got the same size as you expect. And so if you take like ordered monomials in ERs, you get E lambdas. And as lambda ranges over all partitions of width less than or equal to L, the E lambdas give you a basis. Okay. And these Schur polynomials, these S lambdas give you another basis, and there's an odd analog of Koska matrix. And so, you know, it's kind of the remarkable amount of stuff goes through. But this failure of this to be a Frobenius extension, it's the first place, and merrily going along developing odd analogs of everything breaks. And then here's the fix. So the fix is to pass to RL. In fact, this is just commutative. Turns out this quotient is just looks like ordinary even symmetric polynomials of half the rank. And then what you do is get the right deal here. Algebra from before, base change. So just tensor over O sim L with RL. It's important I've done this on the right. And so before O sim L embedded into this guy, now I've base changed, RL embeds into this thing. Now RL is just ordinary commutative algebra. This trace that I wrote down before, when you remember the trace was a right O sim L module homomorphism. When you base change, you get this right RL module homomorphism. But RL is commutative now, so there's no point saying right. This just gives you a projection of an RL module of here onto this guy, and the specializations of my S lambdas and my sigma mu's give a pair of dual bases, and you think it's great, now I fixed everything. But there's still a problem, because this guy is not an algebra. We're specializing, but this specializing, you can think of it as quotienting out by a left ideal. If things were commutative before, when we specialized to the field, we get cohomology of Grassmannians, that was everything was commutative. This left ideal was a two-sided ideal, but here no more. So no good. I can't say this is a Frobenius algebra over here, because this is simply not an algebra. So the fix to that is not at all obvious, but it turns out there is an algebra structure on this space. It's not evident straight away. So I'm going to call this algebra OHNL. So this is odd equivariant cohomology of the Grassmannian. It's the odd analog of our HNL from before. Here's the definition. Take odd symmetric polynomials on the first n variables. Take the tensor product, this braided tensor product of superalgebras with this ring of scalars, this commutative ring RL, and then factor out the following relations. Is it -1 to the S H R minus S tensor ES for all R bigger than n prime. So that looks a bit hard to swallow there. So this is H in the first tensor on those first n variables. This is E, or rather the image of E in this commutative quotient RL here. So this is the E on those L variables in the second part. So impose those relations. If you're kind of familiar with the usual story for Grassmannians, those all look familiar relations. And then it turns out that there's an isomorphism of RL modules between now this is an honest algebra, right? I've taken an RL algebra, this guy, and I've quotiented out a two-sided ideal. Turns out this is exactly isomorphic to this as an RL module. Isomorphism is kind of the obvious thing. It takes A tensor B, I mean the image of that in this quotient algebra. So how do we get it into here? Well, it takes it to A tensor 1. That's an element of this guy, right? So O sim n just tensored 1, tensor B. That induces this isomorphism from that quotient algebra. And using that, you can, if you want to think of it, you can make that into an algebra, but I prefer, there's my algebra. And if I compose that isomorphism with that trace, RL embedding into this OHNL is a Frobenius extension. That's absolutely right. I'm crazy that I write it this way, but I write it this way because that's the classical formula. So whenever S is odd, ES is simply 0 here. But I still find that helpful for me. Okay, so that's fixed. Somehow now the story's begun. We've got this appropriate algebra, which is somehow this odd analog of equivariant cohomology of Grassmannian. The evidence that it's correct is that it is indeed a Frobenius algebra over the appropriate boundary. Now, of course, now since RL is commutative, you can specialize further. If you specialize RL to a field, that gives you an algebra which is sort of the odd analog of this co-invariant algebra, the odd analog of ordinary cohomology of Grassmannian. And that was studied already by Ellis, Khovanov and Lauda, but somehow getting this correct equivariant analog is a bit surprising, and there it is. Okay, so I've got to tell you about bimodules. That's really what this is all about. We've got our algebra, OHNL, but the story is really about bimodules over this algebra. Let's move on to that part of the story. So now let's go back to the even case and think about what we're trying to do something in analogy with. So now I'm going to assume that L is n plus 1 plus n prime, changing my convention a little bit. And what you look at in the even story is that tensor product. So this is OSIM n1 n prime. And sitting inside there, you have OSIM n plus 1. And you also have OSIM n. I don't need any O's because this is the even story that I'm telling you. Sorry about that. The O's are going to come back. So this is invariance under Sn cross S1 cross Sn prime. And this is just taking more invariance, either in the first n plus 1 variables or the last n prime plus 1 variable. So there's this algebra. This algebra is a Frobenius extension of this subalgebra by my fundamental theorem. And it's also a Frobenius extension of this guy. So I'm going to use the notation UNL when viewed. This guy is, of course, what I was calling HN plus 1L. And this guy is what I was calling HNL, this algebra here. So these are our old equivariant cohomology algebras. And this being, since both of these are subalgebras, I can view this big commutative algebra as a bimodule over these subalgebras. And I'm going to call it UNL when viewed as an HN plus 1 HNL bimodule. And I'm going to call it VNL when it's viewed. Everything's commutative, so it really doesn't matter, but I find it helpful to distinguish. Tensoring with these bimodules, this is a right module over OHN and the left module, I'm still writing O, aren't I? So that's habit for you. It's a right module over HN and a left module over HN plus 1. Tensoring with that bimoduling gives you a functor between the module categories of HN and HN plus 1. And I call that functor E. And tensoring with V, which is a right module over HN plus 1, that gives you a functor in the other direction. And I call that F. Now, think about E. What E is really doing is it's taking an HN module. You can think about this functor E from HN mod to HN plus 1 mod as first inducing along that Frobenius extension and then restricting along that Frobenius extension. And F is the other way. It's induce, then restrict the other way. And when you have a Frobenius extension, induction is isomorphic to co-induction. So it's biadjoint to restriction. So it's kind of automatic in a canonical way, adjoint pairs of functors. So it's kind of this beautiful situation. I've got to tell you just a tiny bit more in the classical case, and then I can write down the odd analog, which is very quick after that. So this classical story, what's going on here? So I'm going to look at the Grothendieck ring, or the Grothendieck group of the categories of HN modules for all n. Now, HN is just this just looks like a polynomial algebra. So it's got one indecomposable graded projective module up to grading shift, which is just the regular module. So K0 of HNL is just Z. Everything's graded, so it's really Z, Q, Q inverse, where Q is the grading shift in this story. And then I've got these functors E and F, which go between, since they're biadjoint, they're biexact, they take projectives to projectives, they give me linear maps between the K0s here. And each K0 is just one dimensional, and E's and F's give me linear maps in each direction. So what could it possibly be? I kind of think this is the classical fact, which is why this subject's so rich. Categorifies the L plus 1 dimensional representation of SL2. So if you pass to Grothendieck groups of all these algebras for all n, all of those Grothendieck groups are just free of rank 1, and we've got these functors E and F from tensing with these bimodules that I set up. At the level of Grothendieck groups, you can see that the commutator relations are just the commutator relations of SL2, just acting on its standard irreducible representation. This would be the highest weight space of highest weight L. This would be the lowest weight space of lowest weight minus. Okay, so I've got about 5 minutes to tell you the odd analog of that. Right? So this is something kind of this truly fundamental. So much rests on this kind of most basic and clean categorification of the simplest representation. This structure appears just in so many different places. So we want to go back to the odd case. So now I get to put my O's back, right? Okay, so you can take that tensor product. It makes total sense. It contains my, it doesn't, does it? Because to get those guys, I had to specialize. Okay, so I guess we specialize. Just tidy up a little bit. So this guy I call VNL. No, this wasn't this guy. This was isomorphic to the specialization of that. So I've got to clear off all of that. This is still the right analog of that bimodule. And there is still, this is F. There's still a left action and a right action of these two odd equivariant Grassmannian cohomology algebras. Remember OHNL, it was defined as O sim n tensored RL and then some quotient. And the stuff in the sim n part just acts as left multiplication on that O sim n part. And the RL stuff, which is commutative, just acts by right multiplication. And this gives you a well-defined left action. And similarly, there's a well-defined right action. This is O sim n plus 1, which embeds into O sim n tensored O sim 1. This just acts by right multiplication on the n plus 1 part. And that makes this guy into a bimodule, that's V. And then there's a bimodule called U, which is a bimodule the other way around. Well, to define that, this is a little bit more weird now because things aren't commutative. So it turns out the right way to define that, we have to flip everything around, and you just take the specialization on the left. And now this, for example, this right action of OHN, it comes from the right action on here, but you need to incorporate some signs in this right action, which I'm not going to be able to tell you about right now. So this gives you a bimodule the other way around called U. It's slightly subtle because things are now not commutative. You really have to work here. And then you get these functors E and F tensing with these bimodules. All I have to do is put O there, right? There we go. And you expect hopefully these guys are biadjoint. It's not quite true. E is left adjoint not to F, but to some parity switch of F. There's this Z2 grading around, and there's a parity flip functor. And the other way around, F is left adjoint not to E, but to pi to the n prime E. So you work quite hard, and you can't do this cheaply like before, where you could just think of them as inducing and restricting along Frobenius extensions. As far as we understand, we don't have any analog of a rank 3 kind of partial cohomology algebra here. We only have this Grassmannian cohomology. So we literally have to just prove from scratch that these are adjoint both ways round. That doesn't work either, no. It's sort of, it really feels like there's some obstruction stopping you going from Grassmannians to anything more general. So hence the title odd Grassmannian bimodules, not odd Zergel bimodules, for example, or odd singular Zergel bimodules. I'm just about done. I need to stop. So let me wrap up here. So there's this kind of very, very magical and remarkable odd parallel of this whole story. And you wonder, what do these guys categorify? Well, now we're working not just with graded modules. Gradient shift was Q. We've also got Z2 grading. The parity shift is called pi. So actually these appropriate Grothendieck groups in the odd case are not just free ZQQ inverse modules of rank 1. You get this slightly strange kind of enlargement. If you were looking at Grothendieck groups of graded modules, they would be modules over ZQ, Q inverse. Q is grading shift. Parity shift, of course, pi squared is 1. So you actually work over this slightly larger ring with this pi around, but they're still free of rank 1, and you still have these E's and F's, but the commutators, you get extra pi's appearing. So you don't get quite UQ-SL2. You get what's called UQ pi SL2, which is this thing that's called the covering quantum group of SL2. So it's a slight, if you specialize pi to 1, that's ordinary quantum SL2. But you can also specialize pi to -1, and in that story, it's actually quantum OSP 1,2. It's a rather strange object here, and that's what this odd theory categorifies. That kind of gives you a glimpse of the most important stuff. What's really going on? Let me just write one last thing. A long story. We're looking at this L+1 dimensional representation of quantum SL2 in the even story. If you take if you look at two weight spaces, look at the -k weight space and the k weight space. This is just this SL2 string, -k, k. So two weight spaces that are conjugate under the reflection S in the Weil group of SL2. In the quantum world, there's this braid group action. If you look at this element T, this makes sense as an endomorphism of this UQ-SL2 module. These are the quantum divided powers of these guys. And we're kind of categorifying this L+1 dimensional representation. And in the even story, there's this magic complex of bimodules. You remember E and F to the 1, they correspond to my bimodules U and V. They're also divided power analogs of U and V, which correspond to these divided powers. And there's this rather wonderful thing called the singular-Rouquier complex, which is a complex of bimodules, where you put this in degree D, this bimodule in degree D. Q is it's a complex. So this is the degree D spot, and then you take all D. Tensing with that singular-Rouquier complex, it makes sense as a function on the homotopy category of the categories of modules that we're looking at over these Grassmannian cohomology algebras. So singular-Rouquier complex induces this homotopy equivalence, which categorifies this action of the braid group on this SL2 module. And the whole point of the story is to get an odd analog of that. And it works. That's all I can report at this point. There is indeed an odd analog of the singular-Rouquier complex, and it gives a homotopy equivalence between the bounded homotopy categories of projected modules over these odd equivariant Grassmannian cohomology algebras. Somehow that's a big deal because, well, in the even story, these homotopy equivalences were used by Chuang-Rouquier in a famous paper. Ultimately, from them, they extract derived equivalences between P blocks of symmetric groups. And they prove something called the Brouet conjecture for the symmetric group. Well, in this odd story, I mean, it's a huge long story from here. It's about another 50, 60 pages to kind of set it all up. But in the odd story, it all goes through at that point, mimicking the Chuang-Rouquier arguments in this odd setting. And the final culmination that you get is a proof of the Brouet conjecture for blocks not of symmetric groups, but of double covers of symmetric groups. So somehow this odd analog of the singular-Rouquier complex is exactly what you need to get derived equivalences between blocks of double covers of symmetric groups in characteristic P. That's kind of the final result. And I want to just rework this out, kind of following this story with these Grassmannian bimodules independently. Ebert, Lauda, and Vera have a somewhat different approach. I mean, the kind of core ideas are similar, but they use rather different tools. So the overlap's kind of relatively minor. Now I've got to shut up because I already overran.
Question for Jonathan.
So the way you treated the even case, the same as the way Chuang and Rouquier did it, or is
not
this?
Really. I mean, they didn't really work with. In the background is a Nil-Hecker algebras. So this use of Nil-Hecker algebras. I mean, they had cohomology of Grassmannians there, but they somehow constructed this in a rather different way, not using nil-Hecke algebras, but using ordinary Hecke algebras.
Okay.
And but you can kind of reverse engineer. Somehow you have to, at the end, you have to prove that this complex has cohomology all in concentrated in top degree to prove that it gives you these homotopy equivalences. And in our approach, that becomes a really silly calculation. You have this complex of bimodules, and each bimodule has a basis given by some tensor product of a pair of Schur polynomials. And so in the end, proving that the homology vanishes in all but one degree turns out to be the sort of computation you're very used to with partitions. You're in the end using some kind of odd analog of Peary rule to literally check that the kernel and the image of the differential in this complex are equal, and it's totally concrete. And you can do that same argument you can make in the even case this way, it's a different proof of the properties of this complex in that case.
After Chuang-Rouquier's paper, there was a quick proof for general linear groups. I think that everything worked through finite general linear groups. Do people look at spin covers or projective versions of those things? Would you expect that would also prove?
I mean, somehow Chuang-Rouquier set this up in a kind of axiomatic way so that their theory could be applied in not just symmetric group case, but to many other examples where there's some sort of categorical action going on, including finite general linear groups. This is set up in a similar way. So if you can find some setting where you can see some sort of odd categorical action, you get these derived equivalences. And there is one such setting. It's somehow the general, this is not the finite general linear group, but the algebraic group GLN, which is in Schur-Weil duality with symmetric groups. Symmetric groups are in Schur-Weil duality not with the algebraic group GLN, but the algebraic supergroup QN. And so this theory has all sorts of applications to the supergroup QN or the Lie superalgebra QN, or which I happen to rather like. It's one of my favorite objects, but there isn't any kind of counterpart for finite fields that I'm aware of. I kind of feel there might be something lurking out there with finite unitary groups or something, maybe some blocks that you can't treat that method.
Okay, cool, thanks.
It's a silly question, but it seems that the trick was to insert a 1 into n and n prime.
Yeah, so this way of getting these bimodules, somehow if you kind of think geometrically, this is sort of some correspondence between neighboring Grassmannians.
Sure, but
so you kind of go with this intermediate where you're looking at partial flags with these step sizes, and then you can ignore the middle flag here and you get partial flags of these either way, right? So that's that.
And so can we think doing it with I don't know, other decomposition of L into
so this one, of course, I mentioned these divided powers. If you want to do the d divided power, you replace the 1 there by d. So that's how you set up these divided powers. And in the even story, you can do it not just with Grassmannians with 2 steps and using these 3-step flags to get the correspondences. You can do it with a general partial flag. And these are singular Zergel bimodules. And you can see it's an incredibly rich story in the even world. But somehow in the odd world, all we see is, we don't even see algebra structure here. This is just a bimodule. We only see the algebra structure on the 2-step version, and it's somewhat miraculous that's possible.
Brian?
I have about 5 questions, but maybe I'll discuss one of those. So is there any like geometric thing behind it, like the Grassmannian is behind the?
I don't think so, but I mean, so I think I'm talking again in a mini conference going on in Ottawa. And my title in Ottawa is simply Odd Grassmannians. And that's a complete lie, because there's no such thing as odd Grassmannians. There's only this algebraic shadow of odd Grassmannians, which you feel ought to be out there, but I don't think there's any such thing. But
Okay, and I'll ask one more question. I'll save you Ellis for later. But is there some intuition behind the reason why going to this RL was the right thing to do, like this partial specialization?
There is. so another way to see this, you can kind of see what's going on here. If you look at the this Kac-Moody 2 category associated to SL2. So in the even case, that was defined by Aaron Lauda. And you can see this category of bimodules there as what's called the minimal categorification. So you look at this cyclotomic quotient of the Kac-Moody 2 category. And there's an odd analog of that Kac-Moody category. That's part of those 50 pages I didn't mention, where you have to use this odd analog of the Kac-Moody 2 category. And so you kind of have this kind of avatar which tells you what the right category is by taking the cyclotomic quotient of that odd Kac-Moody 2 category. So you see this ring RL there. If you look at Aaron calls this the algebra of bubbles. So if you in this odd Kac-Moody 2 category, you look at the endomorphisms of just an identity morphism, and that is exactly you exactly see not OSIM, but this largest commutative quotient of OSIM is what shows up there. So somehow that's where the clues come from.
We should stop and allow for final discussion. So thank you very much.